In this lecture, we're going to test for measurement invariance, also known as factorial invariance, as well as compare latent means across the groups. Measurement invariance is really a critical topic with instructional equation modeling, and in general for that matter. Whenever you compare two means or regression coefficients, correlation coefficients, whatever you might want to compare within statistics, you're always making the assumption that those scores are created in the exact same way across groups. For example, if you want to compare management styles for males and females, and you do a simple t-test, you're making the assumption that those scores were created in the exact same way for both males and females. Typically what one would do is just sum those scores, get the mean of those scores, and then do a paired independent samples t-test. However, that's a problem if you do not have measurement invariance. Measurement invariance assumes that your factor loadings and intercepts, or thresholds if you are categorical, are really equal across your groups. So the first important term to remember is what's called metric invariance. And that's testing whether all your factor loadings are equal across all of your groups. For example, if you have 5 items creating management satisfaction, you really have 5 factor loadings. Invariance assumes, or tests, whether those 5 factor loadings are equal across males and females. Because if they differ across males and females, that means your scores are being created differently for males than for females. The next common term we're going to talk about is called scalar invariance. And the scalar invariance basically is testing whether your intercepts or your tau coefficients are equal across groups. It's really important to remember that when you use ML or MLR, you're testing whether the intercepts are equal across groups. In other words, that factor scores are being estimated based on the equation using the factor loadings and those intercepts, just like you would in a regression model. However, if you were to use WSMV or WLS, remember it doesn't estimate intercepts anymore, it estimates thresholds. So your thresholds, those cut points in that latent distribution, are being tested for scalar invariance. So if you're using WSMV, you test whether the factor loadings and your thresholds are equal across groups. So measurement invariance would mean that you have both metric and scalar invariance, which basically implies that those scores, those factor scores, and ultimately in the end most likely your mean or observed scores, are equal across groups. If you don't have invariance, that means the factor scores are being created differently depending upon which group you're in. There's 2 common ways you can test for measurement invariance. The most common one, and we'll focus the most on in this class, is multi-group CFA. In this case, you can test for both metric and scalar invariance. The problem is you can only focus on groups and not look at continuous variables. A mimic model, you can actually look at, you can use continuous variables in multiple groups. You can use multiple groups for multiple CFA too, but it gets very cumbersome if you have more than 2, 3, or 4 groups. The mimic model can actually look at as many groups as you wanted to. So a lot of limitations with that method. Most importantly, you can only test for equality of the intercepts and not whether the loadings are equal across the groups. I'm sure you're all familiar with what ANOVA does in independent samples t-test. You base testing whether the means are equal across 2 groups for independent samples t-test or 2 or more groups for the ANOVA. You could test the exact same question using a multi-group CFA model. However, there are several advantages to using the multi-group CFA model. Although not stated here, one obvious advantage, you actually test the quality of your factor structure or your measurement model before even comparing those means. So you can test, are those means even valid even for a single sample. But let's say you want to look at two samples and compare those means. Well, again, you always assume when you do an ANOVA or an independent samples t-test that those scores were created in the exact same fashion across groups. For an ANOVA or independent samples t-test, you have to assume that's the case. You actually can't test it. So your multi-group CFA, you can actually test for measurement invariance and test, well, were those scores created in the exact same fashion for both groups. You don't have to make the assumption. The other benefit to multi-group CFA is you can adjust those means for measurement error, which as a result will increase your power and provide you with a better parameter estimate, whether it's structural or a mean difference. Again, ANOVAs and correlations, t-tests, and everything else assume your variables are observed, which is often not the case. It assumes they have perfect reliability, which is also not the case. And it also assumes that you have measurement invariance, which isn't often tested. So there's a lot of benefits to using this kind of a model. Here's your typical model that you would see when using structural equation modeling. You basically, what you're really testing is whether that covariance matrix is equal across both groups. Now we can test every single thing about that covariance matrix, the factor loadings, the intercepts, the means, the variances, error variances, everything. But for the most part, all we really care about for measurement invariance is whether that pattern of factor loadings is equal across the groups, whether the latent variable are equal across the groups, most importantly those means of those latent variables equal across the groups, as well as are those error variances equal across the groups. Here are the actual equations we're using when testing for configural, metric, strong, and strict invariance. As you can see here, wherever a G is subscripted, it assumes that those are estimated freely across both groups. So for the configural invariance model, again, this is the model where you basically have the same factor structure across both groups, but there's no constraints. As you can see here, the lambda has a G next to it, which means the factor loadings are estimated equally across, or just estimated across both groups, and they're not constrained to be equal. Same with the factor variance, as well as your covariance matrix, your gamma, and your theta delta. Those are all assumed to be estimated freely across the groups, as well as your mu, subscript G, your tau, and alpha. Everything is estimated freely across both groups. However, both groups have the exact same factor structure, but again, the parameter estimates are just different across both groups because there's no constraints. Again, the configural invariance model is your baseline model, which you're going to be used to compare to the other three invariance models below. As you can kind of see here, the weak invariance model constrains your factor loadings to be equal across the groups, but that's it. You still have a different covariance matrix, taus, mu's, sigmas, everything else is going to differ across the groups. The only thing you're constrained to be equal across the groups is your actual factor loadings here, your lambdas. Our next models are strong or scalar invariance model. For this model, we're only going to test whether the unstandardized factor loadings and intercepts are equal across the groups. Everything else is free to be different. Our next model is our strict invariance model, and here we can see that our unstandardized residual variances are also constrained to be equal across the groups. Typically what you're going to do though is you're going to test for first your factor loading invariance, or your metric invariance. And once that's invariant, you're going to test for scalar invariance. So in this case, your thresholds and your factor loadings would be equal across the groups. And then your strict invariance would then have your factor loadings, your intercepts, and error variances fixed to be equal across the groups. Again, in the bottom one, you can see that because there's only G's next to the covariance matrix, the psi matrix, your mu, which is basically and your alpha, which is your sample, your factor. Where before I gave you the more equation-based interpretation of the four models, here's more of a conceptual basis. So again, your configural invariance model is really your baseline model. We have the exact same factor structure, but whatever you fix or free in one model, you fix and free in the other model. So you're estimating the exact same model, and as a result, should have the exact same degrees of freedom. Your metric and factorial invariance model, also called your weak factorial invariance model, basically requires your unstandardized factor loadings to be equal across the groups. So basically the contribution of every item on the factor is the exact same. For scalar or strong factorial invariance, here now you're requiring the intercepts to be equal across the groups. Remember, the intercepts are unstandardized, and they're basically your indicator means. So you're testing whether indicator means are equal across the groups. Your strict factorial invariance tests whether your unstandardized residual variances or error variances are equal across the groups. When testing for measurement invariance, we often follow these 6 steps, but this order is not necessarily required, and people will test them in different sequences. But the first couple are imperative. So the first thing, one that everyone agrees upon, is that you should estimate each sample separately. So basically you assess the model fit for both groups and make sure they both have a good model fit and large factor loadings, basically good factorial validity, before moving forward. So if you have 2 samples, you have 2 CFA models. Step 2 would be your configural invariance model. Again, that's your baseline to compare it to all more restrictive invariance models. Again, your configural invariance model only tests whether the factor structure is the same across the groups, but not you actually have the exact same factor loadings, intercepts, means, or anything else. Your third and fourth steps, that's a little bit more controversial. Typically, I will test for metric and scalar invariance in tandem, all at once. So I'll force the factor loadings and the intercepts, or thresholds, if we had it categorical, to be equal across both groups. I will then compare the model fit for the metric and scalar invariance model to the configural invariance model. If that changing chi-square is non-significant, I know that both my factor loadings and intercepts are equal across the groups. If that changing chi-square is significant, then I know that either the factor loadings and or the intercepts differ across the groups, at least one. So then what I'll do is I'll look at the modification indices. Again, you only want to focus on those that were constrained to be equal. So any other parameter that would improve the model fit, you do not want to estimate. You only want to focus on the factor loadings and intercepts that were forced to be equal across the groups. You would then relax those constraints one at a time until the changing chi-square was non-significant. The other option you could do is you could relax just the factor loadings or just the thresholds. What I typically do is estimate or relax the entire item. So if I feel that item 3, let's say, is non-invariant or differs across groups, I'll relax both the factor loadings and the intercepts all at once. However, if you prefer, you can only relax just the intercepts or the factor loadings if you'd like, if that's the actual problem with the model. The next step, which is number 5, is testing whether your error variances or residual variances are equal across the groups. That's not commonly tested. The reason is that when creating the equation to create the factor score, the factor scores are being created by your factor loadings and your intercepts. So the fact that your error variances might be different across the groups doesn't impact how that factor score is actually computed. So that one's optional. The 6th step here, which you might want to test, is whether your variances, your covariances, or even your means are equal across both groups. Again, remember, if you use WSMV, there will be no error variances. Those are not estimated in the model. So you could definitely not test for step 5. It's only possible with ML and MLR. In this example, we're going to test satisfaction across 750 employees using maximum likelihood estimation. In this case, we have the exact same sample size for both males and female employees. Typically, you'd prefer relatively equal sample size across both groups. If not, your parameter estimates may be more stable for one group versus the other group. Perhaps most importantly, though, what's going to happen is for your configural invariance model, the sample with a larger sample size will actually carry more weight in that configural invariance model than the one with a smaller sample size. So one option you could do here is if your ends are very different across the groups, you could take a random sample to get relatively equal sample sizes. But again, as long as they're not off by too much, you should be fine. But in any case, we have 9 items, each measured from using a 0 to 8 scale. It's a single measure of satisfaction. Remember, we could use MLR here or WSMV, but we're going to stick with ML because it's much more simple and easier to demonstrate when doing invariance testing. However, you could easily use MLR and you could compute the change in chi-square based on the Satori-Bettler change in chi-square, or use WSMV using the diff test with an M+. One last thing important to remember is that you use MLR, you're assuming variables are continuous. Again, you're using WSMV, you're assuming they're categorical, and therefore you're going to test quality of thresholds. And again, step 1 is we're going to assess the model fit for males and females separately. If you want a good model fit, we want large factor loadings. In this case, we actually focus on the standardized factor loadings. But remember, invariance testing focuses on the unstandardized factor loadings. Step 2 is going to be our configural invariance model, which is going to be the baseline model in the weighted combination of the male and female sample. Again, it's the least restrictive, because actually, although the factor structure is the same across both groups, thus is why it's called an invariance model, there is actually no equality of any. In step 3, testing for metric invariance. Again, that are the unstandardized factor loadings, also called slopes or metrics, equal across the groups. The tricky part here is you have to decide how you're going to set your scale. Remember, you can set your scale by fixing a factor loading equal to 1 or a factor variance equal to 1. This is important in variance testing because you're fixing them to be 1 for both groups, say male and female. So if they're both 1, then of course that factor loading is going to be equal across both groups. But the question is in reality, are they really equal? Conversely, if you fix your factor variances to 1, you're making the assumption that your variances are equal across both groups. So it's really important that you do some test to determine whether it's really appropriate to make the assumption that one of those 9 factor loadings are equal across the groups, or the variances are equal across the groups. As a result, here, just randomly picking one factor loading and fixing it at 1 is really inappropriate. Typically what I'll tend to do is look at my mean scores and figure out whether my variances are equal across the 2 groups. In other words, I test for homogeneity of variance. If those variances are equal across the groups, I feel relatively comfortable, again not guaranteed, that the factor variances would also be equal across the groups. If I feel less confident there, what I'll tend to do is I'll estimate the model separately for both males and females, and I'll look at my unstandardized factor loadings, and I'll pick that unstandardized factor loading and I'll fix that at 1, which is the most equal across the 2 groups. In other words, if my factor loadings are relatively equal for males and females on item 3, I might fix that one at 1 for both groups and test the other factor loadings for invariance across the groups. While you can certainly follow my recommendations, determining whether you should fix the factor loading at 1 or fix the factor variance at 1, arguably a better approach is to follow what was done by French and Finch in 2008. What they basically do is test all possible combinations. In other words, they'll first set the first factor loading at 1 and look at how invariant the other items are. Next, they'll fix the second factor loading at 1 across the groups and see how well invariant the other items are. Next, they'll fix the third item to be 1 across the groups and see whether the other items are invariant. After they test all possible models, they then pick the single item which has the factor loadings that are most invariant across groups. The one that's the most invariant across the groups, they'll make that their reference indicator and fix that factor loading at 1 across both groups. In our step 4, we're going to test whether the intercepts are invariant across groups for the continuous indicators, or whether your thresholds are invariant across the groups if your variables are categorical. You can follow the exact same recommendations we've talked about in class before on whether you want to treat your data as categorical or continuous. And sometimes it might not be a bad idea to test whether the model is invariant across both groups using WSMV and maybe MLR. It's kind of like see how generalizable your results actually are. If your unstandardized factor loadings and intercepts or thresholds are equal across the groups, it's now appropriate to actually compare those latent means. If some of the factor loadings or intercepts differ across the groups, you then relax those based on modification indices and test what's called a partial invariance model. Basically what that means is that most of your factor loadings and intercepts are equal across the group, but a few of them aren't. If an item has a very different factor loading or intercepts across the groups, you have a couple choices. You can compare the means based on the partial invariance model, but the problem with that is that the equation being used to create the factor scores is going to differ across your groups. Again, because for at least one of those items, the factor loading, intercept, or factor loading and intercept differ across the groups. The other option could be you might just want to drop that item, thus resulting in an invariant model. The approach you take really depends upon the type of measurement you have. For example, if you're in an instrument development phase, it might be a good idea to drop items that are non-invariant or that differ across groups. However, if you're using a very commonly used measure that's well published, used a lot, in that case, it might be a good idea to test for a partial invariance model. With that said, if you want to be very thorough, you might test how different the means are based on a partial invariant model, and after you drop that item and have measurement invariance, how different are those means when you do have invariance. It's an approach I often take, as I want to know what are the consequences of either dropping the item or using a partial invariant model. Assuming your factor loadings and your intercepts or thresholds are equal across the groups, you've already compared your means, you might then want to test whether your error variances are equal across the group, or maybe your factor variances, if those weren't fixed at 1, or maybe the covariance between those factors are equal across the groups. You really can test almost any research question you want within an invariance framework. However, for this class, at least this lecture, we're going to focus more on the factor loadings and intercepts. Later on, we'll show you how to actually compare path coefficients or structural coefficients and test whether those are equal across the groups. Nevertheless, our next model will focus on whether the error variances are equal across the groups, which again, you may or may not want to test. This is just basically a few reminders for you. If you're going to use ML, you can compare the difference between two chi-squares. But the question is, did you violate the assumptions of multivariate normality, independence, and everything else? If those assumptions are violated, you probably want to use the MLR test, or WSMV, depending on whether your data are continuous or categorical. Just remember, if you use MLR, you have to use a strictly positive Sator-Bentler chi-square difference test, or the diff test procedure if you're using WSMV. When looking at model fit for invariance testing, it's actually a relatively controversial topic, very similar to model fit within a single sample. There's basically two different camps. Some people look at only the changing chi-square across the model. So, for example, how well does the configurable invariance model fit compared to a model where you have your factor loadings and your intercept constrained to be equal across the groups? If that changing chi-square is significant, some people will tell you to relax it. However, as you guys all know by now, your chi-square and your chi-square difference tests are basically related to the complexity of the model as well as your sample size. So you have a huge difference, a huge sample size for both groups. Even a very small difference between those two groups might be significant. As a result, some people, like Chen, recommend you look at the change in. And these are the basic standards that Chen recommends. One important thing to remember is that while these standards work relatively well with ML and MLR estimation, they should not be used for WSMV. Again, so the question would be, you look at whether the change in CFI is greater than 0.01 for your factor loadings. If that change is greater than 0.01, you would say your factor loadings are not invariant and they differ across the groups. Where if your change in CFI is relatively small, based on their standards less than 0.01, you would say your factor loadings are equal across the groups. And the same argument can be made for your intercepts. Step 1 is fairly easy to do with an M+. You follow the exact same process we have in class previously. There's only one minor difference. In this case, we're going to analyze the model fit and evaluate the factor loadings and other parameter estimates for each group separately. In this case, on the left-hand side, we're going to look at only females, and on the right-hand side, we're going to look at only males. To do this, the only difference would be we're going to use the use obs sex equals 0 on the left-hand side to tell M+ only select those in the sample who are female and estimate that model. On the right-hand side, we're going to use the use obs sex equals 1 to estimate only males in the sample. Before we move forward, let's comment on a few other things in the code. Again, we're going to use ML estimation, and we're going to estimate the factor loadings for all 9 items. In other words, we're not going to fix any of the unstandardized factor loadings at. This will allow us to test whether all 9 items have equal or unequal factor loadings across the groups. Another change we're going to do is we're going to correlate the error variances for M1 with M2. So I really want to know whether those error variances are significant either for one or both samples. We can also, at a later time, test whether those error variances are equal across the groups. Lastly, I'm fixing the variance for our satisfaction variable at 1. So again, I'm making the assumption that my variances are equal across both males and females. If that's not the case, after we've estimated both models, we then want to evaluate our model fit as well as our CFA model results. Again, you want to look at your standardized factors and make sure they're all large. As you can see, the model fits well for both our males and our females. It's critical here to make sure your degrees of freedom are the exact same for both your males and females, because you want to make sure you're testing the exact same model. Again, recall our sample size is equal for both males and females, and therefore we shouldn't be too surprised that chi-square is relatively similar, which again suggests the model fits the data well for our males and females. In step 2, we're going to test for configural invariance. There's a couple of new additions to our code here. The first thing is that grouping is sex. 0 equals female, 1 equals male. You're basically telling M+, estimate a model for females and males simultaneously. Our first model is going to be our female model. Our second model below it, where it says model male, is we're going to estimate the model for males. So again, the first model statements is our female code, and the one right below it, under model male, is the model for males. So in both cases, we need to make sure we're estimating the exact same model. A couple of very important things to note. SAT by M1 star, M2 to M9 is really the exact same thing as the model we're testing for males below. SAT by M1 star, M2 to M9. One big difference is that by default, M+ will estimate your intercepts and your thresholds for that matter. So under the model statement for females, I didn't tell M+ to estimate the intercepts, although I could have, but I know it's going to do it by default, so I didn't worry about it. The difference is for the males, I have to tell M+ to estimate those intercepts. It's important to note that by default, M+ will fix the factor loadings and thresholds to be equal across groups for the second group, in this case our females. So I have to tell it to estimate the factor loadings and intercepts. If not, it will fix them to be equal or invariant across both groups. Just like our female model code, we have to tell M plus to fix the variance at 1 for both males and females. And because we correlated M1 with M2 for our females, we also need to estimate the error variance between M1 with M2 for our males. Again, this is our configural invariance model. So we're testing whether the model, the structure itself, is the exact same for females and males, but nothing is constrained to be equal across those groups. The first very important thing to notice is that the degrees of freedom is 52. That's 26 for my male sample and 26 for my female sample. Another very important thing to remember is that when using ML, which will not be the case with MLR or WSMV, is that your chi-squares are additive. So you can look at the chi-square for the female sample and the male sample separately, add them together, and you'll get the overall chi-square. Another great piece of advice that I always do is after I run each model, both the configural invariance and my metric and scalar invariance models, just to be safe, I always copy the unstandard results and I paste them into Excel, and I make sure the results are different across both groups. Because it's very easy for M plus to constrain them to be equal across groups if you're not being careful. Because remember, the default in M plus is to constrain your factor loadings and intercepts, or thresholds if using WSMV, to be equal across the groups. In any case, you can see that, as you might expect, the overall chi-square is significant, but your CFI, TLI, and your RMSEA, and even your RMMR are all within the acceptable range, suggesting you have a good model fit for your configural invariance model. Basically what this is telling you is you have the exact same factor structure across your male and female sample, and as a result, it's okay to test a more restrictive invariance model. In this case, we're going to start by testing whether our unstandardized factor loadings are equal across the groups. So as I said before, by default, M plus will fix the factor loadings and intercepts to be equal across the groups. As a result, as you can see under the male model, I commented out the fact that I want my factor loadings to be estimated. Consequently, my factor loadings are now fixed to be equal across groups for this code. But again, under the male model, I'm still estimating or freeing the intercepts, and the rest of the code remains exactly the same as your configural invariance model. In this case, all we're going to do is compare the chi-square for the configural invariance model to the factor loading invariance model. As you can see here, the change in chi-square is non-significant. And the most important thing to notice here is your degrees of freedom are 9. So you have 1 degree of freedom for every unstandardized factor loading. Given that your chi-square is non-significant, you can now assume that the factor loadings are equal across the male and female samples. And thus, they contribute equally to those factor scores. Our next model is the intercept invariant model. So here you can see I removed from my code both the factor loadings and the intercepts for my male model. Again, the default is to fix them to be equal across the groups. The rest of the code is exactly the same. With one exception. Here, I'm actually fixing my factor mean to be 0. By default, m plus will fix the first sample, in this case our female, that mean to be 0. And by default, it's going to estimate the second sample mean for males. Here, I actually want to fix it at 0 because I'm only interested in comparing the unstandardized factor loadings and intercepts. And right now, I do not want to compare the means. Later on, I can relax that assumption and then test whether the means are also different across the groups. Now these are the results for the model testing whether the factor loadings and intercepts are equal across groups. So a couple different approaches you can take here. What most people will do is compare this model back to the configurable invariance model. You're basically testing whether the factor loadings and intercepts are equal across the groups. As you can see, your degrees of freedom are 18. You have 9 degrees of freedom for your 9 factor loadings, constrained to be equal across the groups, and you have 9 degrees of freedom for each intercept, which was constrained to be equal across the groups. Our change in chi-score is about 19, and our p is equal to 0.3652. This basically suggests that you do have metric invariance, and that your factor loadings and intercepts are both equal across the groups. Again, remember, you're comparing unstandardized factor loadings and unstandardized intercepts. What you can also do, if you'd like, though, is test whether your model where you have the factor loadings and intercepts invariant, you can compare that back to the model where only your factor loadings are invariant. So essentially what you're really doing is testing whether at each stage, what's the change in chi-square. This is useful when you want to test things in stages. So basically, what's the change in chi-square from the configurable invariance to the factor invariance model, factor loading invariance, to the factor loading and intercept invariance model. As you can see here, our change in approximate fitness is also relatively small. So again, the change in CFI, TLI, RMSEA is relatively small. Again, these results suggest that the model, the factor loading and intercepts, are invariant across groups. This is critically important because that means the factor scores are being created in the exact same way for both males and females. As a result, you're comparing apples to apples. If your factor loadings or intercepts were different across the groups, you're now comparing apples and oranges because the equations being used to create the factor scores for males and females. Here's a simple example of when you have invariant slopes and intercepts. As you can see, the relationship between your latent variable and each indicator is the exact same across both groups. You can interpret the unstandardized factor loadings as meaning the slopes are the exact same across the groups. The intercepts, it's a little bit more tricky, not too bad though. If your intercepts are equal, it basically means you have no difference between your groups when the latent variable or latent factor is 0. Here's an example of a non-invariant intercept, but with an invariant slope, or factor loading, if you want to think about it from that perspective. So the factor loadings or slopes are invariant because the change in the latent variable and the change in the indicator variable is the exact same. However, you can see that the intercept is much lower for females than for males. And what that basically means is your indicator variable is lower for males and females. So on average, females have a lower mean score on that indicator variable, that item, than do males. So you could ask yourself, what is it about that individual item that results in males scoring higher than females, especially if the other items are all equal or invariant across groups? Here's an example where our intercepts are invariant, but our slopes or our factor loadings differ. As you can see, the relationship between the latent variable and the indicator differ. However, on average, the intercepts are the same across both groups. Again, for those with a latent variable of 0, they had the exact same response on that item. Our next example is when you have non-invariant intercepts and slopes. So as you can see here, the relationship between the latent variable and the indicator differs based on your gender. Moreover, the intercepts or the means of the indicator when the latent factor is 0 also differ. This would be the most problematic because it basically means that your latent variable and indicator have a different relationship to one another, and the overall response to that item also differs across both groups. Assuming your unstandardized factor loadings and intercepts are invariant, the next thing you might want to do is actually to compare the means to test whether males and females satisfaction at work on the latent variable is equal across the groups. To do this, what you typically do is you fix the mean at 0 for one group and estimate the other group. And this will occur by default in M+. Remember, if you want to override this default, you have to fix that mean at 0 as shown here. You can then either look at the changing chi-square or the z-score to test whether there's a difference between the groups. It's a lot easier to look at the z-score as I'll show you in a few minutes. But what you could do is look at the chi-square, changing chi-square when they're fixed at 0 and when they're not fixed at 0. If that changing chi-square is significant, your mean difference. As you can see here, the code's the exact same thing we had before when we were fixing our factor loadings and intercepts to be equal across the groups. The only thing I did here is I removed the default. I kept the default, which is to free the factor mean for males. So by default, the factor mean for females will be fixed at 0. And I'm going to estimate the factor mean for males. Because the factor mean for females is 0, it's creating the exact same factor scores for males and females. Because again, remember, you have equal factor loadings and intercepts, so we're going to create the factor scores in the exact same way. The estimate of the mean for males is really the comparison between males and females. As you can see here, the mean for females is fixed at 0, and for males, that mean is negative 0.116. Again, these are unstandardized units, therefore males would be 0.116 units below females, and this difference is not significant at the 0.05 level. If that difference was significant, you could then say the score is significantly lower for males than for females. But again, our p-value is equal to 0.168, so that difference is non-significant. After you've compared means, in terms of whether there's a significant difference between the groups, the next thing you might want to do is test, well, is the effect size of the latent mean comparison, is that meaningful? For example, if you have a few thousand people, you might find a significant difference between males and females, but from a practical standpoint, that difference might be very small. As you may have learned in your past stat classes, your Cohen's d is computed by taking the difference between your two sample means and dividing that by your pooled standard deviation. So you're basically testing how far apart are those two means in standard deviation units. The exact same equation can be used for latent mean comparisons. For a latent d, or latent Cohen's d, you're basically comparing your two means, the difference between those two means, which in this case would be alpha 2j minus alpha 1j, and dividing it by your pooled standard deviation. In our example here, remember, we fixed both our factor variances at 1. As a result, we've already standardized our variable, and the variance is 1, and as a result, the square root of a variance of 1 is equal to the standard deviation of 1. Consequently, our estimated mean of males from M plus was a negative 0.116. Minus 0, remember 0 is the factor mean for females, and we're just going to divide that by 1. So a effect size of negative 0.116 basically means that males are 0.116 standard deviations below females. So a relatively small effect. If for some reason you decide not to fix your variance at 1, which again may be very justifiable if your variances really aren't equal across the groups, you could then use the above equation. And your n's are already given to you, so you know what those are, and your variances are also provided by M+, so it's relatively easy to compute. Our next model is we're going to test whether the error variances or the residual variances are equal across groups. Now it's important to remember this is not an assumption of measurement invariance typically, only if you want to have strict invariance. Again, strict invariance is when your factor loadings, intercepts, and error variances are all equal across the groups. But again, only your factor loadings and your intercepts are being used to create those factor scores. To do this is a little bit different than we had before. As you can see, the new code we have is M1 in parentheses 1 semicolon. Now that's going to fix the error variance to be equal across our males and females for item M1. M2 in parentheses 2 will make the error variances for M2 to be equal across the two groups. Same thing happens. So basically, the parentheses from 1 to 9 are all telling M plus have equal error variances for both my males and females. The other thing I did here as well, which wouldn't be a requirement, is I'm fixing my factor means to be 0 for both my males and my females. I can justify this because there is no significant difference between males and females in terms of their factor mean scores. However, if there was a significant difference between males and females, I'd want to relax that. Because if I force them to be equal across the groups, and they're really not equal, it's going to result in a larger change in chi-square, and potentially result in a misinterpretation of your error variances if you're not careful. As you can see here, our change in chi-square with 9 degrees of freedom is equal to 9.385, and that change in chi-square is non-significant. What that basically means is your error variances are equal across the groups. Remember, you have 9 degrees of freedom for each of the 9 error variances you fix to be equal. We have 9 degrees of freedom here because I'm comparing the model where I had the factor loadings and intercepts invariant to this model here where the loadings, intercepts, and error variances are all equal across the groups. Again, the fact that they're all equal across the groups means you have a strict invariance model. To test for structural invariance, which is basically the structural coefficients, or the relationship between your latent variables, it's actually quite simple. And we're actually going to show you how to do that in the path invariance demonstration. However, just like the measurement invariance, all you're going to do is compare the model where the paths or the structural coefficients are invariant to a model where they're not invariant, and you're going to assess the change in chi-square. Again, it's very important to remember that you have to have metric and scalar invariance before testing for structural invariance. The reason being is if your factors aren't being created the exact same way across males and females, in other words, you have either a different factor loading or intercept, that's going to create a different factor score, thus making the comparison of your structural coefficients inappropriate because they were computed using different equations. The one thing I cannot stress enough is to always make sure what you intend to be fixed or free is actually free or fixed for each model. And this is why I always copy the results out of M+, paste them in Excel, often right next to one another, and I'll compute a difference score between the two. So for example, if I fix my factor loadings to be equal across males and females, the difference in those factor loadings should be 0. If I'm estimating the intercepts, that difference will likely not be 0. Another important thing to remember is always, always, always check your change in degrees of freedom. It gives you a great indication of whether the changes you made to the model are appropriate. For example, if you're fixing the factor loadings to be equal across the groups and you have 9 items, you should have a change in degrees of freedom of 9. When presenting these results, I also often put them in a table and make it very clear what models we compared to which one. And it's easy to base that off a change in chi-square. As you might be able to imagine, full invariance, full measurement invariance, is often not the case in practice. So the question is, what do you do if you don't have full invariance? As talked about before, you can relax some of the assumptions, and those factor loadings are different across the groups, allow them to be different. And the same thing for your intercepts, and therefore result in a partial invariance model. There's a fair amount of literature out there on this. You can read the Byrne 1989 is a great resource for you. However, what I often do is I want to understand how big of an impact are the different results when I go from a partial to a full invariant model. For example, if I'm comparing my means, I might compare my means when models are assumed to be invariant, or when models are assumed to be partially invariant. And I might also compare the results to a model where I remove the items that are not invariant and see how comparable they are. For the most part, if the results don't differ, I often just estimate the partial invariant model and indicate that to the reader. In the end, the important question is, what are the implications if you violate the assumption of measurement invariance? In other words, if the scales aren't invariant, but you assume they are, how big of an impact does that have on your mean comparisons across the groups or your correlations across the groups? So remember, you can compare any statistic, not just are the means different across the groups, but for example, you could test the correlation between X and Y the same across the males and females. Here's going to be our in-class practice problem, which would be a little bit more difficult than we've done in the past. What makes it more difficult is that we're going to test a two-factor CFA model with data that are now categorical. So because our data are categorical, we're going to use WSMV estimation, and we're going to test where there are unstandardized factor loadings. And now we're going to use our thresholds and not intercepts because our data are categorical. And we're also going to test whether the covariance or the correlation between are factors equal across the groups. So as you can see here are the items that go on the BM and IM factors. The other thing that makes it a little bit more challenging as well is, unlike ML, we can't just subtract the two chi-square statistics to get our change in chi-square, but instead we have to use the diff test procedure with an M+. However, to make our lives a little bit easier, we're going to assume the factor variances are equal across the groups. To test this model, we're going to follow basically a 5-step process. The first thing we're going to do is estimate the elementary and middle school models separately. So basically we're going to test first the elementary school teachers and test for elementary teachers, do the BM and IM scales have a good model fit with large standardized factor loadings. We're going to do the exact same thing for middle school teachers. Our next model, our configural invariance model, remember, now that's a weighted combination of the elementary and middle school teachers. Again, for your configural invariance model, it assumes you have the exact same factor structure, but you're allowed to have different parameter estimates. In other words, your factor loadings are going to differ across the groups, your thresholds, your means, the correlation between the factors, they're all going to be different because there's no constraints. The only invariance part is you have the exact same factor structure with different parameter estimates. Our step 4, we're going to test for metric and scalar invariance in tandem. This is what M+ recommends you do. This is what I often do, whether I'm using WSMV, ML, or MLR. I test them in tandem, and then if the change in chi-square is significant, I'll use the modification indices to figure out whether which factor loadings or either thresholds or intercepts differ across the groups. We're also going to test for a partial invariance model if needed. And lastly, which really requires a 6 here, I'm also going to test whether covariance is equal across the BM and IM. So basically, I'm testing, is the relationship between BM and IM equal across elementary and middle school teachers? Here's some example code that we're going to use to test for invariance within M+. I provide this code for a couple reasons. The first reason is that for the most part the logic and the steps you're going to follow is the exact same thing you did when we did ML just previously. The only difference is that now we have thresholds we're going to estimate and not intercepts. Just like before, for our second sample, in this case our middle school teachers, we need to estimate the factor loadings and the intercepts. Here it's done within brackets. So you can see here you have BM1 $1 means estimate the first threshold for BM1. BM1 $2 means estimate the second threshold for BM1 and so forth. So you want to estimate all our thresholds. Another important thing to remember is that you need to make sure that your thresholds are equal across the groups. This is critically important. So if elementary school teachers have three thresholds for BM1, there needs to be 3 thresholds for the middle school teachers. Because if not, you're estimating different models if you have a different number of thresholds across the 2 samples. The other addition here that we need to focus on is our saved data. Because remember, we need to use the saved data to compute the diff test. We also need to use the analyze diff test is to actually compute the diff test procedure. So remember, we're going to save the data for our comparison model, and the analysis command here is going to be used to compute the change in chi-square for this model compared to another model. So that'll be a little bit more tricky as well, but it'll give you a lot of practice using the diff test procedure within WSMV and comparing models.